All right, line A1, learning task 9, we're going to take a look at inductors inside of a DC circuit. And I do want to go and highlight that we are going to learn about inductors inside of a DC circuit right now. We are also going to go and cover inductors when they get into AC circuits. We're not getting to there yet, but we will be there in a couple of days. And so what you need to do is you need to compartmentalize this knowledge that we're going to go and have right now. When we finish up the inductors at DC, you need to go and hold on to that as being DC. Inductance. So be very careful about the way that you memorize this. Be very thoughtful and intentional in making sure that you remember that we're talking about what's happening inside of here, that we're talking about stuff that is going to go and happen inside of a DC circuit. There is going to be a little bit of crossover. There's always a little bit of bleed where, circuits that are in DC behave similar to some circuits that are inside of AC. We'll clarify that as we go along there, but this is all strictly DC theory here. Let's talk about a theoretical inductor. If we take a look at a circuit like this, and we know that we don't have a theoretical inductor because they're all, practically speaking, made out of wire, and since they're made out of wire, they're going to have inductance. But if we could go and have a theoretical inductor that only had pure henries of inductors, and that was it, and if we placed it across a source like this, we know that we would have to go and satisfy KVL. KVL is short form. You're going to see it all over the web and things like that for Kirchhoff's voltage law. And Kirchhoff's voltage law simply states that the sum of all voltage drops has to be equal to my source voltage. So for me to be able to go and do that, I would have to have whatever this value of volts is, if that's 12, I would have to go and drop that across here if this were to go and close. The only way that I could go and drop 12 volts across here would be if I had something that would go and satisfy this formula, E equals negative L delta I over top of delta T. This is another one of those formulas that's missing all those deltas off of it. If we gave ourselves a couple of values, we could figure out that we would be able to have a fixed value of delta I over top of delta T. Let's say that this thing over here was a 12 volt source. So if I needed to go and satisfy a 12 volt drop over here, I would need to have 12 volts out, negative 12, which would be equal to L. Let's go and give ourselves a Henry value here of 2. 2 times delta I over top of delta T. We don't have a value of delta I over top of delta T, but if I were to take a look at it, I would be able to go and describe that as something that would have to be, 6 amps a second. If I had 6 amps per second, that would go and give me this ability to counteract, with 12 volts in there. What that would look like is that would look like a straight line, something like this. I'm going to have a rise 6 amps over top of, 1 second that I'm going to go and get out of it. And this would only work if we had a theoretical inductor and we had a theoretical source that could just continue to go and dump those amps out, because our current would have to go off into infinity. We would always need to be increasing our current in order to satisfy that equation that we just looked at over here. E is equal to negative L delta I over top of delta T. Up top there, sorry, I was just trying to erase that. It's not going to be practical for us to go and have that, to have a ever-increasing current. First of all, we don't have a source for it. And secondly, we know that it's just impossible to build an inductor without using wire. And wire is going to go and have resistance that is going to be based upon its K, the type of material, times its L, all over top of the circular mill area, or the AWG, the wire gauge that we are going to be using. So in practicality, we are always going to go and see practical inductors that are going to go and have a small component of resistance inside of here. Let's take a look at one of these as a practical inductor now. Over here we have given ourselves a 120 volt DC source. We've given ourselves a 15 ohm resistor over here. We've given ourselves an inductor. Once again, we need to satisfy Kirchhoff's voltage law. The sum of all volts is going to be equal to my source voltage when I go and close that switch. The instant that I close this switch, the amount of current that I'm going to go and have is going to be 0. At the exact instant, we're talking like instant. The instant that I close that switch, we will have 0 amps inside of that circuit. We've got voltage, but the electrons themselves have not started to go and move inside of there. I'm just going to start a little graph over here on this side. We're going to call this thing amps. We're going to go and call this thing time. And then right below that, we're going to go and build ourselves another little graph that is just going to be the switch, okay? So I'm going to go and have the switch between closed and open. Open is going to be low, right over here, when I close that switch, the switch is going to move to its closed position. So that line translates up top over here. So initially, when the switch was going to be open, we would have 0 amps flowing through. It's an open circuit. That just kind of makes sense. We're not going to have 0 amps going through. The instant that we go and close that switch, we're going to go and have 0 amps. That is going to be going through it. If I have got 0 amps going through this resistor, V is equal to I times R. This is Ohm's law. Volts is equal to my current multiplied by my resistance. And if my value of current right now is 0, that means that my value of volts that I must have being dropped across it would also be 0. Which means that the only other place left inside of the entire circuit for us to be dropping volts is going to be over top of this friendly little beast over here. That's our inductor. So we're going to go and drop the instant that we close in, we're going to go and drop 15 volts, all 15 volts across that inductor. We're going to be dropping 0 volts. That is going to be across that resistor. I'm just going to go and put these here because we're going to watch these numbers. They're going to be dynamic. They're going to be changing as we go along. That's at the very instant that we close off. Now what happens is there is going to be current that is going to start to flow, right? We got a negative, we got a positive. Current flows from negative to positive. So I'm going to have current that's going to start to go and flow. As that current starts to flow through here, this is an inductor that is going to go and fight back against a rising current. Refer to what we covered in the previous learning test where we saw as the current is rising, that it's going to be pushing back against it. So what it's doing, in effect, is it's going to be slowing down this current that we are going to have over here. We're not going to have, full values of current right away. Our current has to push through. We're going to work with that same analogy before of the big linebacker. Okay, here's the big linebacker. It's a beefy linebacker, and our little linebacker that we are going to go and have over here as well. But that little linebacker is going to slow the big linebacker down. But if you've ever seen a matchup that looks anything like this, whether it's football or anything else, where you've got something large, the instant that these two collide, come together, there's that point of instant, there's going to be maximum stopping. But then what happens is as this small linebacker starts getting overpowered, we start to see the big linebacker picking up speed. He's able to go and force through much faster because he starts to build momentum on this section going in the opposite direction. It's maybe a poor analogy, but it shows what's happening inside of here. What we're getting is the instant that we close in, we get a little bit of movement. The instant that these two make constant, a little bit of movement. But then it's going to go faster and faster and faster as this linebacker develops more and more power, more and more flux, so to speak. So our current, when we look at it, starts out at a value of 0 initially. Then my current starts to go and rise. Okay, let's bring this thing up to a value of 1 amp. If my current goes up to 1 amp, that's an I, 1 ampere over there, and if that's multiplied by 15 ohms, I know that this would therefore no longer be 0 volts. This is now going to go and be 15 volts that we are going to go and have over here. And so what I'm going to have is if I'm dropping now 15 volts over top of this, that would mean, I wrote 15 here at the very beginning. I don't know what I was doing there. I confused with this one over here. That should have been 120 volts. That's 120 volts at the instant that we closed in. All the volts were dropped across there because that was from there. I just grabbed the wrong value. I'm sorry. These things happen because I'm trying to write and talk and, keep ahead at all at the same time. It gets a little overwhelming for me at times. Anyways, back to this over here. We see that we've got that 120 volts that we initially had. Now we have 15 volts of it dropped across here. According to Kirchhoff's law of voltage, we need to drop all of the source voltage across these two. So I would be dropping 105 volts across there, right? The difference between what I have over here. And my current is going to go and continue to increase. It's not going to increase quite as fast because what happens now is it doesn't have to have as big of a counter EMF. E is equal to negative L delta I over top of delta T that we are going to go and have, right? At this point where I've gotten all the way up to here, now there's less voltage that it has to go and counteract. It's only got to have 105 volts. Therefore, since the L is a constant, it's just going to go and lower its slope of the line. So we're going to go and have a different slope. Now, it's going to be a lower value of slope. And so what's happening is my current is increasing. We'll increase the current all the way up to, let's take it up to, we'll take it up to 6 amps right now. By the time I get my current all the way up to 6 amps, 6 times 15 is going to go and take me all the way up to 90. That would mean I'd be dropping 90 volts across here, which would mean that I would be down to dropping 30 volts across here. So I'm going to go and have my current that has increased right now, but by the time I get all the way up to this point where I'm dropping now only 30 across here, that means that counter EMF only needs to go and develop 30 volts, right? That's the only way that an inductor can oppose any change in current is through that counter EMF. And if this is a fixed value, L, based upon the turns, then that would mean that the only way for me to go and drop the amount of counter EMF would be to go and drop that delta I over delta T. And so once again, I'm going to go and lower that slope on the line. Eventually, we're going to get to what we refer to as steady state current. And the steady state current that we are going to have is going to be when we are dropping all 120 volts over top of this. Once we get to steady state current, there's no longer any change in current. The current is no longer increasing through this inductor. Therefore, the inductor is no longer going to go and be active in the circuit. It's like it just steps back out of the circuit and it's like, okay, my work here is done. The current is no longer changing. I don't need to do anything. It still has energy stored around it in the form of a magnetic field, but it's no longer active inside of that circuit. They give us a couple of graphs that go and demonstrate this over here. They show, the way that this thing starts at the instant that we close that switch, that we're going to start out at 0 amps, and then we're going to go raise that all the way up to its steady state current. We'll call that thing ISS. ISS is always going to be steady state. We use that subscript of the double S's for steady state in all sorts of different electronic and electrical components. What I'm also seeing is that my voltage, and this is another graph, they're just showing it over top of the same amount of time. My voltage, initially, I'm going to have a negative 120 volts. This is my counter EMF that I'm seeing over here. Starts out at a negative 120 volts, but then it drops all the way down to a value of 0. And it corresponds, it follows the exact same line as this one over here. This graph is able to be analyzed based upon something that is called our time constants. And a time constant is found off of using this little formula. T, which is the Greek letter tau, is equal to my L divided by my R. In other words, the amount of inductance that I have inside of my circuit over top of the amount of my resistance. The more inductance that I'm going to go and have, the shorter the taus are going to be, the more or the less inductance that I'm going to have, the longer that they are going to go and be. And what tau is it's a measurement of the amount of time that it would take to reach steady state current if I continue to rise at that initial slope. Remember, at the very initial time when we turned that circuit on, we had a really, really steep line over there. So I measure that off of tau, or I don't have to measure that off of tau. I can calculate that off of tau. This has already been measured and verified and formulated into this formula that we're going to be using over here. Tau is going to go and be a super, super crucial formula for doing a lot of our calculations. We do measure our circuit inductance in henries. It's a physical thing based upon the henries. We measure our resistance in ohms that we are going to go and have. And then I'm able to go and have tau. Now this tau is just going to be time constant. It doesn't matter what value of voltage I'm placing over top of that circuit. I'm always going to go and take 5 taus to go and reach what we call steady state current. In practicality, it's an infinite line. It's always going to be getting closer and closer to the steady state. It never actually quite reaches that. It just slows down. But because it's so small, after 5 time constants, we say that it has reached steady state current. What's happening is every time we are rising 63.2%. By the end of the first tau over here, let's draw that line right like that, we've risen to 63.2% of our steady state current. In the next tau, what I'm going to do is I'm going to go and rise to 63.2% of the remainder. So this one over here should be showing a little bit higher, but this one should be 63.2% of this column that we have over here. And then inside of the next tau, I'm going to be doing the exact same thing, rising to 63.2% of the remainder, etc. And it goes along like that, and every time we're just rising to 63%, 63%, 63%, and then 63%. But by the time we get through all the way to here, we just call this thing steady state current. Once we reach steady state current, we have to look at our inductor itself and say what's happening inside of this circuit. I'm just going to go back to this one that we have over here. I'm just going to erase a bunch of what we had around it so we can analyze it. It's a lot of erasing. Oh well. Okay. When I've got steady state current, so this thing is going to go all the way up to 8 amps of steady state current. I'm going to have current that is traveling through here. Because the current is no longer changing, there's no longer going to be any fight that's going to be put up by my inductor. So it travels all the way through here, travels through that resistance, dissipates some heat as it goes through it. We'll draw some little heat lines coming off of it. And then returns back through that switch to the source itself. This is going to go and create magnetic lines of flux that are going to be around my conductor. Now we know that we can go and use that left-hand rule. We can establish our magnetic lines of flux around any conductor. You know, this one over here, we can do a left-hand rule up there, but that's only going to be a single set of magnetic lines of flux. What is this component? Well, this component is a collection of wires that has been built with the express purpose of creating magnetic fields to use them for, you know, these inductive purposes that we're going to cover off inside of here. Which means that the amount of magnetic fields that are going to be inside of here are going to be compounded. You remember that formula that we had? L is equal to n squared mu A over top of little l. This is the thing that defines what an inductor is. We've got all these turns, which means that we're going to go and have all of these flux lines that are going to go and be linked. Around the outside, excuse me, of this inductor over here, we are going to have a stretched out field that is going to be waiting. Now we know that according to the law of energy conservation, energy cannot be created nor destroyed. It can only go and change form. So what we have done is we have taken electrical energy, actual movement, we've converted into magnetic energy, and then we are converting that into stored energy over here. We're just going from active energy usage to stored energy usage over here. When it's stored like this, it's not going to dissipate anything. It just sits stretched out around the outside, and we wait for something to go and happen inside of this circuit. We can actually go and, you know, quantify the total amount of energy that we are going to have inside of here. There's a formula for it. It's on your ITA worksheet, but it says that W is equal to 0.5 L times I squared over here. In other words, the amount of energy that is going to be stored, and this is energy in joules, even though it shows as being watts over here, but the energy that's going to be stored in joules is equal to half of my inductance multiplied by the maximum, or my peak current that I'm going to have flowing through this inductor. That's going to be my steady state current for any one of these. This is a phenomenal way for us to go and store energy and deliver energy back into a circuit. What does an inductor do? Well, it opposes any change in current. When the current was trying to go and increase, we saw that it was trying to go and fight back against it. I'm going to go back to that drawing that we created in last video where we showed the current that was going to be rising, and then we showed steady state, and then we showed our current falling again and what that was doing, and we kind of broke it up into 3 sections: the rise, the steady state, and the fall that we had over there. And this was for a conductor that had current that was traveling into it like that. And what we saw during the rise, you can go back into the other video and verify it, is that during the rise we had a counter EMF that created a current that was opposing, coming towards us. We're going to indicate that with the dot. And during the falling current, when my current through the main conductor was falling, then what I saw is that my counter EMF made some small little currents that were going to go and try to aid this one over here, because they want to oppose any change in current. When the current was at that level, that's what the inductor dreamed of being able to keep it at, so it was collapsing lines of flux back in to try to maintain that. When this was rising, it tried to oppose that over there. This energy that's stored in the magnetic field is going to go and do this. Note how when I've got this drop in current over here, I simultaneously am having induced currents, small ones, that are going to be aiding my main current. Let's talk about what happens when we open up a switch, because it's a really dangerous thing if done incorrectly, but it's a really useful thing if done properly and correctly. When we open a switch, we know that it's not actually an infinite amount of resistance. We treat it like it's an infinite amount of resistance, but in reality, it's just an air gap. And if you've ever watched high voltage videos, you know that air can be ionized and turned into an arc, and it can turn into a conductor. When air turns into a conductor, it's dangerous. It's going to be operating between like 3,000 all the way up to 30,000 degrees. This is hotter than the surface of the sun type of temperatures. It's going to cause massive thermal expansion of copper. A cubic inch of copper will go and fill up to the same volume underneath a 3,000 degree arc. A solid cubic inch of copper can expand as large as it's about a 20 by 20 by 10 room. It's still solid. It's just an expanded solid at that point, right? So we get massive amounts of damage that can go and happen. So when we open this switch, we have to treat this switch as if it were a resistor, not as if it was a open that could not be passed. Because what we're going to have is that the second that we try to interrupt the steady state current, this inductor is going to fight that. And it's going to fight that by collapsing all of its lines of flux back in on itself really, really rapidly. And in doing so, it's going to try and generate a large enough voltage to bridge that gap. Okay, let's go through this over here. Right now, we've got it closed, got our 8 amps going through. I'm just going to remove that one that we need. As soon as we open this over here, what we now have is we have got a 500 K ohm resistance that is going to be inserted inside that. It's 500 K because of the air. Okay, we're just measuring the value of that. 500,000 ohms. This thing wants to maintain that same 8 amps to go through it. Well, if we're going to go and work off of Ohm's law, which we always do, V is equal to I times R, what it would need to do to go and overcome 500 K ohms at 8 amps, 8 times 500,000, is going to be a value of 4 million volts. We call that 4 megavolts, MV. That is a phenomenally high value of voltage. Obviously, this is going to be dangerous. I mean, nobody wants to get hit by 4 million volts over here. But when we don't understand that our inductors or coils of wire are storing energy in their magnetic lines of flux, and we open them up, boom, you're guaranteed there is going to go and be some sort of kickback that's going to go and happen inside of that circuit as this thing collapses those lines of flux back in on itself to try to induce a large enough value of voltage to bridge that gap. It wants to maintain 8 amps. It's not going to be able to. It's going to go and run out of energy. It runs out of magnetic lines of flux, right? It's going to have only a certain number of magnetic lines of flux. Once it uses them all up, it's used them all up. It's like a trust fund baby, right? It's got a whole pile of resources, and if it rapidly uses them all up, that's it. It's out. So we're going to go and have that off of this field over here. It's going to get pulled back in super, super rapidly. We call this thing inductive kick. We'll use it in some places. Some places we want an arc. Igniters, DSI, direct spark ignition, is a very common thing when we're working with gases. Gas furnaces, gas-driven appliances. Oftentimes we don't want to run a pilot light, but we want to go and run an arc that is going to go and collapse. If you've worked with a barbecue sparker before that, or a electric stove, you've probably heard an inductive circuit at work, that tick, 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 tick sort of noise that you get whenever one of these is sparked up, is simply going to go and be an inductive circuit that is opening and closing, and every time it's trying to maintain its current across that air gap, because that's going to be the easiest place for it to try and put it across, and tries to put it across the air gap, and that's what creates our sparks inside of there. We will refer to this as inductive kick. Sometimes you'll also hear it referred to as voltage spikes or switching transients. Switching transients is a term that's used with BC Hydro's power that they're supplying. They're supplying, stuff through transformers, and transformers are big coils of wire. Whenever they switch transformers on and off line to go and balance the grid around the province, there is going to be some of these transients that are going to come through. They can be very, very damaging to all sorts of pieces of equipment. So what we do need to do is we need to go and snub that or shut that down somehow. There's a bunch of different places where we have got coils that are going to be seen as being opens that could go and give us this inductive kick, particularly when we work with motors. Once we get into third year, you're going to come back to this theory. You're going to have it solidified, because you are going to go and talk about taking coils and opening them when they're moving inside of a magnetic field, rotating machine. When we do that, we're going to go and get inductive kicks. So a lot of our motor starters are going to go and have these snubbing type of circuits inside of them. Two common ways that we are going to go and deal with that. One of them is going to be using a nonlinear resistance, or what we refer to as a field discharge resistance. Nonlinear resistances mean that their resistance varies based upon the value of voltage. Generally speaking, they're going to go and be something that is in the thyristor family. Thyristor family are resistors, notice how it's the last half of the word resistor, are resistive components that are made out of thyrite or a thyrite type of base, which is a type of element. What these have is they've got a ridiculously high value at a high value of resistance at low voltage. So if I were to go and graph my volts over here, this would be 0 volts, this would be high voltage. When I'm at a low value of voltage, they're going to go and have a ridiculously high value of resistance. But then as my voltage goes up, it drops on one of those universal exponential curves that we looked at earlier. It's not a linear line all the way across. Usually what it is it's a rapid drop. This one's actually probably poorly drawn. It should be more looking like that. So that once we get to certain values of voltage, these things just break right over and conduct. They go to a low value of resistance. We can go and use them inside of these circuits, because if I've got something over here that, let's say it's 24 volts DC supply that I'm supplying something with, when I open that up, it is going to go and try to maintain its direction of current through. It's going to collapse its lines of flux back in, rather than jumping across this, which might be 500 k ohms. It's going to try to jump across this, which might be something like 100 k ohms. We're going to keep these things in the hundreds of k ohms. If this is 100 k ohms, the current is going to take the path of least resistance, it's going to jump across that. And what happens is when this thing induces voltage to break that over, boom, this thing goes into conduction. And it's kind of like having a spring door. When you get a bunch of people going through a door that's got an automatic closer on it, the door just kind of stays open because everybody's just bumping through that thing, and then as soon as the last person gets through, the door closes. That's what these thyristors are going to go and do, is they're going to break it over, send this thing into conduction, send a ton of current through this thing, and then when the current drops below what we refer to as a holding value, then it's going to go back to its high resistance state. During powered on time, when I'm actually running from my main supply over here, the resistance, if it's going to be in the 100 k ohm, is so large that it's only seen as being a small drop. There will always be a little bit of leakage of current going through it. That's just part of what's going to go and happen when we put these things in, but it's not a massive, massive amount. Our more common way of dealing with this is going to be through what we refer to as a freewheeling diode. Freewheeling diodes are awesome. Now, you have covered diodes back in first year. Diode is simply going to be a PN junction. It's going to be a junction between pentavalently doped and trivalently doped types of equipment. It's going to have that little barrier potential across the center. And what we need to do is we need to put it in the proper direction. It's a one-way device that is going to be triggered by voltage levels generally from 0.3 to 0.7 volts. So it doesn't need a lot of voltage to go and put itself into conduction. Here's how they go and work. When I close this circuit, I'm going to have current that is going to be traveling through this inductor in this direction. My inductor doesn't like it when the switch is closed. When the switch closes, it's going to go and slope in that current, but then the current's going to go and hit steady state. And when it's hit steady state, the inductor is going to be fine. It's just going to be dealing with it. It has its lines of flux stretched around the outside like this. At the same time, I see that I'm still supplying power from here, positive and negative, and I see I've got a negative attached over onto this side. This side is called the anode because it kind of looks like A over there. This side over here is the cathode, it's the negative side. But this thing is what we refer to as reverse biased. When we've got a positive on the cathode and a negative on the anode, this thing is going to be blocking. So there's no path through here. When we go and open this circuit, we've got all of those lines of flux that are still stretched. The instant we open that circuit, we've got all those lines of flux that are still stretched around that inductor, and the inductor had current going through in this direction, and the inductor wants to keep it that way. That's what they do. They don't like change. So it wants to keep it that way, so what the inductor is going to do is it's going to collapse lines of flux back in on itself. It will turn itself into a source using those magnetic lines of flux to cut through and generate voltage according to Faraday's law, e.g. is equal to BLV, like that. So it collapses back in. How does current flow through a source? Well, current flows through a source from positive to negative. Remember? Through a load it goes negative to positive, but from a source it goes positive to negative. So it creates its own positive here, it creates its own negative here, and what that does is that forward biases this diode. This diode that was in opposition to the main supply over here will be correctly biased to what we have over here. It's going to go into conduction. And it's going to say, yeah, you want to stick current through? Perfect. This is the proper way that current should go through. And what's going to allow is it is going to allow current to travel through here. This magnetic field is going to go and collapse in on itself, whoosh, like that. As it collapses in on itself, once again, trust fund baby. It's going to run out of resources and no longer be able to generate voltage. So just for a brief little period of time, it's just going to kind of discharge itself through here. We will see these things, freewheeling diodes, far more commonly than we are going to go and see these ones, the field discharge resistors. We will see these ones occasionally, but they're just not as common that we are going to go and see them. Freewheeling diodes or field discharge resistor are both types of circuits that are commonly referred to as snubbers. Snubbers. Or a snubbing type of circuit. It's just designed to snub off or to cut off any type of inductive kick we would be getting out of the circuit. Okay, let's go take a look now at some formulas and some calculations that we're going to go and deal with on these circuits, and then we'll get to our last section of these as well. I'm just going to go and erase a bunch of stuff on here. I'm going to actually just grab a whole pile. Just give me a second. Take that, and we will use the old delete button. Perfect. Okay, we're going to work with a circuit over here. We're going to talk about changes in current and how that's going to go and affect my counter EMF that I'm going to go and have out of this thing. So we're going to go through a couple of just values of counter EMF that are going to come out of here. We're going to be working off of that formula, and once again, it is misprinted inside of yours, but it is negative L delta I over top of delta T that we are going to have here. E is equal to negative L multiplied by delta I over top of delta T. So the first example that they give us is they say, look, what would we do if we got a coil that has got an inductance of 200 henries? So we're going to identify where that goes in. That's going to be, not 200 henries, 200 millihenries, so 0.2 that we are going to have. That's milli is going to be anything that's just to the right of the zero, right? And we haven't talked about this yet this year, so we'll just take a look. This is going to be my milli range over here. Then the next 3 zeros is going to go and be my micro range. And then after that, we go into nano and pico, although we really don't deal with a lot of stuff inside of the nano and pico, so we'll just kind of ignore those. Back to what we had up top here. So it says, coil with an inductance of 200 millihenry has a current through it varied from 1 amp to 6 amps in 20 milliseconds. What's the value of voltage that is going to go and be changed on here? Well, if I had 1 amp, and if I'm now raising that to 6 amps, that is a change of plus 5 amps. Okay? It's not 6 amps because it was already at 1 amp, but now we took that 1 amp and we dumped more current. We're raising the amount of current through it. So it's going to be a value of plus 5. So we're going to go and say it's going to be a value of plus 5 amps. That's the change in current. We're going to put that in as being a plus 5 because it's positive and an increase in current. Over top of a time of 20 milliseconds, because this is 20 milliseconds, we write that as being 0.02, like that. So now I'm going to take this one and 0.2 like that. And so now I go and put it all together inside of my calculator. When in doubt, bracket it out. 5 divided by 0.02 multiplied by 0.2. And when you do that, you're going to go and come out to a value that is going to be negative 50 volts. I want you to go and take a look at that negative symbol that you're seeing off of that 50 volts. That negative is on there for a reason. It's because it is in opposition to my current flow. It was a raising value of voltage. Once again, we'll go to that little graph that we drew there before. At this point, we were at a value of 1 amps, and then we bumped this thing up. When we bumped it up, we then are going to go and get current that is going to be in opposition to our main current. That's our main current. We're going to get opposition. That's why we got this negative, just showing that it's a counter EMF that's pushing back against it. It's the little linebacker. It is going to be defeated. It's a given, thing, but it's going to slow it down a little bit. Okay, the next question that they have is going to talk about a dropping value of current. Same deal, we're going to go and use the same formula. E is equal to negative L delta I over top of delta T over here. And it says, what about if the same coil has the current through it dropped from 6 amps down to 1 amp? So we're going to go and follow this. We're going to drop this thing back down. Well, if I go from 6 down to 1 amp, that is going to go and be a negative 5, right? We're going from 6 down to 1 amp. They showed in the formula as being the first where we are ending up at minus where we started out at. And they should do the same on the other one as well. But you can just look at it and say, if it's dropping, it's a negative amount of current. So I'm going to put that in as being a negative 5 amps. They're saying that we're doing this thing through the same amount of time, 20 milliseconds, 0.02, and that we're using the same coil, that we are going to go and have a 0.2 Henry coil. Take all of that, put it into your calculator. When you do put this in, don't forget that negative ahead of there because it's a negative L. When you do put that in, what you should note is that this negative over here and this negative are going to cancel each other out, which is now going to go and leave us with a result that is going to be plus 50 volts. This is critical as well, that this is a positive, because this tells us that the counter EMF, the voltage that is being induced to try to fight against that change in current, that it is going to be aiding our original circuit. We saw that, once again, working off that graph, we saw that we had an aiding type of voltage when our current was going to be dropping. So basically, if you want a short form, what we've just covered inside of here, when the current is rising, it's going to fight against that rise by putting voltage back in the opposite direction. When the current is falling, it is going to fight against that voltage fall by putting voltage through in the same direction that we are going to go and have. The next two that they are going to go, or the next three that they're going to have, are going to go and deal with the fact that when we change, if we change the speed at which we go and drop our current, or raise our current, then we're going to go and see large amounts of voltage. They say, hey, what would happen if we'd use the same coil again, so a 200 millihenry coil. Let's just erase all that. Except this time the current is going to go and vary from 6 amps to 1 amp, so a negative drop in 2 microseconds. Well, milli going into micro is going to be a completely different set of zeros in front of there. So negative 0.2, that's my Henry's value, multiplied by a value of negative 5 over top of delta I, which is going, or sorry, over top of delta T, which is going to be 0.000, that's my milli, and now we're into the micro, 0.02, like that. So you punch that into your calculator. When you do that, you're going to find that now our voltage changes. We're using the same coil. Now we're going to go and see 500,000 volts, 500 kV. So the faster my current is going to go and change, the faster that this thing is going to be affected. The last two are going to just be simple formulaic manipulations. I'm not going to go through those. We'll just explain what they are, but you can go do the calculations yourself because they're not as critical to the theory. What we just covered in these, a fast change results in big voltages, and that this thing is going to go and oppose a dropping current or it'll oppose a raising current. That's the critical theory for us to understand of this. The rest of this is just formulaic manipulation. Can you find the value out of it? They say calculate the inductive coil that produces a back voltage of 400 when the current changes from 80 to 30 amps in 0.1 of a second. Well, if you go through that one, you should be able to go and figure out your change in current. It's going to be a 50 amps, a negative 50 amps over top of 0.1 of a second, and then just from there, work everything backwards and through there. It'll come out to that 800 millihenries that we're going to have, and then they do the same thing on example number 5. They say what rate of change of current would cause a voltage of 200 volts to be induced in a 300 millihenry coil. Once again, they're just going to go and isolate for my delta I over top of delta T. In this case, it would be 667 amps a second, which seems really large, but you got to remember, we're not probably hitting 667 amps a second. If I were to take that seconds and divide that down into milliseconds, that would mean that we would have 1/1000, so we'd have 0.6 of an amp per millisecond or something like that. It's all scales. It's just a ratio that we are going to go and have. Okay, we're going to go and pause this one over here. We're going to jump into another video to cover off the last half of this learning task, because the last half is really starting to deal with a little bit of transformer theory, you know, how we can move over from one side to the other. So we'll deal with that in a separate video so that you can kind of refer to that one separately instead of having to, you know, wade your way all the way back through this.